Okay, everybody, welcome to predicting Oscar winners and box office hits using the things you found on the internet. Deborah Hanus will be giving this lovely talk. Thanks for coming.
Hi, my name is Deborah, and today we're going to talk about how to predict box office hits and Oscar winners using things you found on the internet. Right? Amazing. Anyways, so just to give you some background about how I got here, I did my undergraduate and my master's at MIT, where my research focused on developing computational models of how people perceive things. I spent a year as a Fulbright scholar in Cambodia learning about how education translates into job creation, particularly in the tech sector. And then I spent some time working as a software engineer at a startup out here in San Francisco. And then I decided to quit life and become a PhD student. So now I'm a PhD student at Harvard studying machine learning, where I've worked on a lot of data-related projects. And today we'll sort of walk through a data science project and talk about some of the important components of it. I'm sure some of you have seen this graphic about what data science spend most of their time doing. It works out to, as you can see, about 82% managing your data, sort of boring things. About 13% of the fun things that you think of in data science. And about 5% things so boring that they're totally unmentionable and they don't even include them. However, I think that there's one component that's missing here. So in addition to these data wrangling, exploratory data analysis, and machine learning, I'd say maybe we should break this data wrangling out into two components. Maybe it's 62% data wrangling and 20% just understanding your data and making sure that you know really well what your data set looks like, and make sure before you put it into any sort of machine learning algorithm. Because if you put garbage in, garbage comes out. So a lot of this talk is going to focus on ways of understanding your data. So just to give you an outline of what we'll do here, when you're doing this, you want to first define a question that you can answer, acquire good data, understand that data, and then you can fit a model and analyze the error, and then you can start to draw conclusions from that data. So to start off with, we will define a question that we can answer. So I'm going to ask all of you to pretend that you are producers. And what you want to do is you want to invest money in a movie that is going to make a huge pile of cash. So the question that you really want to know is, will this movie be a box office hit? If I put my money into this, am I going to get a ton of money out? But it's kind of hard to answer that question. So instead we can say, what is the likelihood that my movie will be a box office hit given that it has certain features? So maybe movies which come out of Spain are more likely to do well. Or we could just turn this into a correlation problem. We could say, what attributes of a movie are correlated with box office success? So that's actually the question that we're going to answer in this discussion. Okay, so now that we've defined a question that we can answer, we want to acquire good data. So to start off with, what is good data? Good data it's relevant to the question that we're trying to answer. Ideally, it's relatively structured so that we can, so that we don't have to wrangle it too much and it doesn't become 90% data wrangling. And it's relatively complete so that we don't have to deal with issues in missing data, which is, if you have it missing data, that is like a whole nother talk in how to deal with that. So what are some places that we can find really good data? For this project, we were really lucky and we were able to find some great 90s style tables, which are very easy to scrape. So like an example is Box Office Mojo has some great 90s style HTML tables. Something like IMDb Py is relevant. It has a lot of great movie data. And the nice thing is that it's relatively, you can see you have that HTML box, which always has the tomato score. Or Wikipedia is the best. You can see it also has some, on the right, it has some very structured data of, always like who is it directed by, who is it produced by. So you can know, you can be reasonably sure that you will have the data that you need coming out of that. Or another way that you can find data is also something like IMDb. Okay, so those are some good data sources. So now that we've found it on the internet, how do we actually get it to our computers so that we can do something with it? One way you can do this is using some sort of API, like we used IMDb-Py, which is just a set of functions. You make a function call, which is like get movie by ID, and then you call all of the IDs, and it will give you an object which has all of the information that you want from it. Another is to write, if there's no API, you can write a web scraper. And to do that, what you do is you get all of the text, the HTML, make the text queryable, and bring it down to your computer. So step one here is to make an HTTP request to get the HTML. So we start out with something like this. This is Box Office Mojo. This is a list of all of the top grossing films in 2017. You can see, once again, it is a beautiful 90s style HTML table. And we can also see some interesting things like the URL up there at the top has information about how we can access this information. So specifically, I copied it down and blew it up here for us to look at it. But everything after the question mark is a query parameter, which is giving us some information about what will be on that page. So in this case, there are page numbers. And there's information about what year of movies we're getting. So we could get movies from different years by changing the year. Or we could get, or we could just change the page number and we can get all of the movies from 2017. So I'm going to get all of the movies from 2017. And so here I'm just using HTTP requests and the time function, which is helpful to make sure that we don't make our requests too quickly. And then I'm just make a get call, putting this URL in there, and changing the query parameter to be a different page number. And then I'm putting it into a dictionary, and now we have all of this beautiful HTML on our computer, and we can do things with it. However, the problem is this HTML right now is just a bunch of strings. So you might have to use regular expressions or things like this in order to go through that. But it turns out that people have written libraries which make this relatively easy to make this all this text queryable. So in this case, we have to look at a simple example of when we have something like some simple HTML here, which you can think of as sort of a parse tree where the HTML tag is the highest tag, and then you have a head and a body, and then you have information in there. And so you can use something like beautiful super PyQuery to get each of these elements out of the tree. So you can say something like, get me all of the paragraph tags. And it will get you all of the paragraph tags in that text by searching through it like a parse tree like this. So we can look at this example again. And then we can right-click and view the source. And this is all of that text that we had in our computer. And we can look at this. And this is sort of this is one of the harder parts of data scraping, looking at this wall of text and seeing some sort of pattern so you can get the data that you want. Here, what I noticed is that all of the numbers that I want have the same font. They all are font size 2. So what I did is I found with all of the items with a font size of 2. And it just gave me this list of all of the items in the HTML that I wanted. And so then we can look at a given one of these. And then from looking at this, we can see that it has a link tag, and we just want to get the text out of that. And so then there. Now we have the name of the top grossing movie for 2017. OK. So I know with all of these nice tables, I made this look really easy. But there are a couple of things that you should think about when you're doing this that are pretty common problems that come up. One is a lot of websites will do some sort of rate limiting. They're fine with people clicking through their websites and getting information, but they'd rather not have, get tons of requests for information. So the way you can do this is you can make yourself look more like a human by adding that time element that I had there and say, rather than making requests as fast as you can, just make 1 per second, which is more like a rate that a human can click through. Another is sometimes there might be an API key which identifies who you are. And so that's another thing that you can either make sure that you get if you want to use an API. And then, excuse me. And one of this, I gave this talk recently, and someone told me a great story about this, where they had an open data site, and so they had a lot of information available, but some of the information you had to pay for. And then they had a competitor which would come and scrape the data off of their site. And they wanted to prevent this. So the first thing they did is they said, if you want to use our API, you need to sign up. You need to prove that you're a customer, and we'll give you an API key so that you can prove who you are. But what their competitors did is they found the API, the identifying code for Google's bot that crawls the websites to determine what the rank of the page will be. So then they looked like a bot crawling the site. And so the way this person got around that is they made everything into a single-page app in JavaScript, and then they used Selenium to click through each of these things. So then it's not just HTML that's on the page. So those are some common issues when you're working through this. OK, so the next step is for us to understand our data using some exploratory data analysis. So what are some factors that we can explore here in order to see whether this movie, see what information we have available and see if this movie is going to make money? One is maybe the movie budget. Maybe if you put a lot of money into a movie, you're more likely to get a lot of money out. Another is IMDb rating. Maybe movies that are rated well are more likely to make money. Maybe certain studios like Warner Brothers, sort of like that brand name power behind the movie will make it make more money. Something else that might be predictive is the amount of money that you make in the opening weekend. If everyone's really excited about the movie and they come out right after it opens, then that means that you'll make more money overall. Or maybe there's this sort of like a certain number of opening theaters that is really good. Because if you saturate the market too much, and you're playing in every theater, you won't be able to fill all of your seats. But if you only show in a few theaters, people aren't going to be willing to travel hundreds of miles to come see your movie. So maybe there's some good point here. And then another factor might be seasonality. Maybe people prefer to watch movies when it's cold outside. And then the MPAA rating is like if it's a G, PG, et cetera. So to start off with, we just started with one of the most basic things you can think of to explore the data, which is a scatter plot. And we just looked at the correlation. So here we're looking at the gross revenue, how much money the movie ends up making, versus the number of opening theaters. And we want to see if there's some sort of correlation. And it looks like there is sort of this inflection point where sort of around 3,500 theaters, where the movie seems to make more money. So the number of theaters that you open in does seem like it has some sort of effect, yes. Yeah, it's true. And that is most likely an errant point in the data. And that's definitely something that you should look at in the course of this. We actually did this entire thing was a final class project in my first semester of graduate school. We did everything from collecting data to the whole analysis in a course of the 2 weeks between Thanksgiving and the end of the semester. So there are a few points like that where we could have gone through things a little bit more with a little bit more detail. So here's another one. Well, okay, so gross revenue versus quality rating. So you'd think that if a movie is well rated, it would make more money, and it turns out that that is absolutely not correct. There is no correlation whatsoever. No relationship there. Okay, so here we're looking at the gross revenue versus the opening gross in that first weekend after the movie opens. And it looks like this is actually quite predictive. So you can actually tell pretty well how a movie is going to do overall based on that first weekend. So this is predictive. Okay. So then we ultimately ended up combining some of these factors into a multivariate regression model, which fit the data fairly well, which was predictive. And then, so to recap some of the conclusions that we drew from the data, and you can see all of these in more detail in the Jupyter notebooks, which are all online. One is budget helps, but it doesn't help a lot. Timing is very important. December is actually a fantastic release date. PG and G-rated movies tend to make more, which makes sense. If you're limiting the number of people who can see your movie to over 18, there'll just be fewer people seeing your movie. And money made in the opening weekend is very important. Okay, so we were producers. And we talked about what it would take to make our movie a box office hit. But now we're going to go through a second line of analysis and say, but what does it take to win an Oscar? How do we figure out if this movie is going to win the awards that we want? So it turns out that we'll go through basically the exact same process. So to start off with, we'll define a question we can answer. What we want to know is what makes an Oscar winner. But that still is a little bit vague, and it's hard to answer. So we could say, what is the likelihood that this movie will win an Oscar, given that it has certain features? We could say, what attributes of a movie are correlated with the movie winning an Oscar? And then the next step is acquiring good data. And this turned out to be sort of difficult. So I mentioned IMDb Pi earlier. And what they did is they have this they have IMDb Pi Pro, which you need to pay for. So they don't make all of their data available. They have a subset, which they say is OK for you to use. But they use rate limiting in a different way in that each query takes probably like 10 seconds. So for us to run an analysis over all of the data, over all of the movies that had won Oscars, it was very, very difficult. We had our script running for about a week, and we decided that we needed to do something different and find some new data source. So what we did is we found a set of we found a bunch of data with all of the Oscar nominees and whether or not they won. So what we did for the rest of this analysis, we said, given that a movie has been nominated for an Oscar, can we find features that will predict whether or not the movie actually wins the Oscar? Which is a slightly different question. So we said that. OK, so now we get to explore this data. So what are some factors that we can explore here? One is what was the movie nominated for? So the movie nomination category. We also had thematic content on all of these. So, like, is this about family? Does someone smoke in this? And so on and so forth. And then the movie genre, like, is it a drama? Is it a horror? Is it a comedy? And where the movie was made, as in, well, what country? And when the movie debuted. So this is a plot of the countries most associated with winning Oscar movies, with winning Oscar awards, excuse me. But anyways, it seems like, given that movie is nominated, Italy and Spain are actually very, very likely to win an Oscar. We also looked at the number of movies winning in a given month, and the month that they're released. And as you can see, there seems to be this, oh, my animations don't seem to be working. Anyways, we look at the number of movies winning per month, and you can see that there seems to be this sort of sweet spot of like December, September, and October, where it's much more likely that your movie will win if it comes out near the end of the year, in that period a few months before when the Oscars are awarded. But it's possible that there are just a lot of movies that come out around December. So we looked at the ratio of winning films to the number of films nominated per month. And we can see that still, like, this period of September, August, September, and November seems to yield in a higher proportion of wins. There we go. OK, so now we need to talk about how to fit a model. And so the first thing that we thought about is, what do we actually want from our model in this case? I mean, we want a prediction of whether or not the movie is going to win, right? So we want a binary output, either a winner or not a winner, based on some information. And like I said, this was a class project. We weren't aiming too high, so we said we wanted to be more accurate than some baseline. As accurate as possible. So some potential models are logistic regression has a binary output. And then there are a lot of things that you can do with it. Whether ridge regression, lasso logistic regression, and elastic net regression all describe the type of loss function that you put on it. So how you define your errors. So we tried all of those. We tried some support vector machines. That would be another way that we can get a binary output. By drawing a line, we can say, does it fall above or below the line? And then some ensemble of these methods. So in general, whenever you're making any sort of prediction, the first thing that you want to do is you want to figure out what your baselines are so that you know what you're doing. So we made our two baselines. What if we say everyone that nominated is a winner? Our classifier will have 29% accuracy, which isn't that great. So what if instead we say everyone is a loser? As you might imagine, that one does quite a bit better. Maybe we should stop here. But we didn't, because we're overachievers. So to select a model, it's useful to think about what errors your model is making in order to make sure you select a good model. So remember, we started out with all of these different classifications, algorithms that we could use. And there's a good chance that you haven't seen this since your last statistics or probability class. But it's really, really useful for thinking about what your model is getting wrong. So in this case, you can look at your errors. So in the case where, in this case, we say we have a winner, and our model predicted that it was a winner, that would be a true positive. Or we have a loser, which we predicted to be a winner, that would be a false positive. So one thing that a lot of people do is using these numbers, which you can get by calculating a confusion matrix. You can evaluate how good your model is. In this case, one thing that you can look at is accuracy, just overall how good is it at predicting things. And as you can see, we actually had a great accuracy, okay, a middling accuracy, by saying that everyone is a loser. And then you can also look at recall and precision, which are different ways of describing how well your model did. And then what we ended up using was an F1 statistic, which is defined like this, which is a mixture of this recall and precision to describe how well the model is doing. And one important thing to note is that we use the F1 statistic, but you really need to think about your use case. And would it be a bigger deal for your use case to predict something as true when it's not true? Or would it be a bigger deal to include things which might not need to be included? Like, for example, a common example would be something like fraud prediction, anomaly detection. At which point, if something goes undetected, that's a big deal for the bank because they have to pay money. So whereas if they say, we think that this transaction is fraudulent and it's not, they just call you and it's really no big deal for anyone and just a minor annoyance for you. So in the bank's case, it would be much more likely that they would want a higher number of false positives. Okay, so one common way of looking at how good your model is the receiver operating characteristic. So what you want here, we're looking at the true positive rate versus the false positive rate. So if you have a very low false positive rate and a high true positive rate, that means your model is very accurate. So what you want usually when you plot something like this is you want as much area under the curve as possible. Ideally, if you had something that went up closer to 1, that would be even better. So here we're just comparing 3 types of logistic regression that use these different loss functions. And here it looks like they are basically the same, except the logistic regression with lasso has just a little bit more area under the curve. All of these had approximately 80% accuracy. And so we went through a few more models in our course of process of elimination of doing this. But I think going through those would just be repetitive. So this is the idea. We did this several more times. OK, so now we can draw conclusions. Sorry, that was a little louder than I expected. So as you saw, nominated films in Italy and Spain have a good chance of winning. Films are more likely to win if they're released later in the year. You probably want to tone down the gore unless it's a war film. War films it's totally fine to have lots of blood in war films. And if a film is nominated for Best Picture, then its odds of winning are very good. But if it's nominated for Best Cinematography, it's probably not going to win. Okay. So another important part of this whole developing a model process is thinking in more detail about what exactly your model gets wrong. So just recently there has been more attention in thinking about what data is going into your model and how to make sure that your model is doing what you think it is. So when we're doing this, we should think about what exactly our model misclassified. I think it's very easy when you're running these to say, I put together an algorithm, I did all this data cleaning, I've been at this for hours, and finally my algorithm converged and I have a prediction and the accuracy is reasonable. Let's ship it. But there actually really needs to be one more step of looking at those errors, what the model got wrong, and seeing if any of those errors are systematic. Because there are a lot of problems that can come from that. So there's this one common example of Joy did this great TED talk on this, which is which talks about facial detection algorithms. And most of the training data are for the data sets of faces are mostly light-skinned individuals. So Joy is this researcher at the MIT Media Lab who works with facial detection software, but she has this problem where she can't test any of the software because she has dark skin and it doesn't recognize her face. Instead, she has to wear this crazy mask to make her face light, which doesn't even look like a face, in order to just test the software because she's using this standard software which is trained on these light faces. And a lot of this really just comes, as I learn more and more about fairness, I find that a lot of it really just comes down to really, really understanding your data that is going in and making sure that you have a good array of information in that data set so that it's not learning some weird feature like, okay, faces are light. Another example of this that made the news recently is YouTube was labeling sensitive content, and they labeled some number of LGBTQ themed videos as being sensitive content. And this is an example where it is good to think about what you're doing, because a lot of people within YouTube said that there actually is that this was actually fair because they had the same number of false positives as false negatives, which is actually that is one definition of fairness. But the problem is if you label any LGBT, because this is, these videos are very important to some people, if you label any of these videos that are very important to some people as sensitive content, that is a much bigger problem than potentially leaving some sensitive content unlabeled. So it's not clear what the right thing to do here is, but it's something to think about, which I think illustrates the trade-off of how you could be thinking about this. And so if there's one takeaway from this, it is when you're working with machine learning and you're developing one of these projects, once you think it's done, before you draw any conclusions or tell anyone you've solved a major issue, it's always a good idea to take at least some time to analyze your errors and look at what exactly your model is getting wrong. Okay, so in conclusion, what did we do here? We defined an answerable question. We built a web scraper. We explored the data. We fit a model to the data. We analyzed our errors. And as I said, I did all of this as part of a team of 4 people. I told them I was giving a talk, and I asked them to send me pictures. And all of them sent me pictures of birds. And that was when I knew I had a great team. So in terms of next steps, as you're learning about web scraping and putting together a data science project, what we used here to build the scraper is requests and Beautiful Soup / PyQuery. For analyzing the data, we use Jupyter scikit-learn stats model. Another great way to learn how to do this is to look at example projects. All of this data came from Jupyter Notebooks and Oscar Predictor GitHub.io. And we just tried to really step through everything we did and how we were thinking about it as simply as possible. So that might be a good place to go and start some data analysis. And then if you have any questions, feel free to reach out to me. There's my Twitter.
Thank you, Deborah. So now we'll take questions. It'd be nice if everyone could just line up and we can pass the mic around up here if anyone has questions.
Hello, nice talk, by the way. Thank you. So you had mentioned several different models that you could use, logistic regression, support vector machines. So how did you end up choosing between them? Is there some knowledge of the data and what the models are capable of that helps you do appropriate selection? Or is the technique mostly start trying models until you get a fit?
Sorry. The technique that we used was what models do we know that will give us what we want, which is this binary output, and then process of elimination. By fitting everything and saying which one performs best. So our Jupyter Notebook actually goes through this whole process of elimination. The best I actually did not show here. It ended up being a random forest classifier. It definitely can. It tells us another thing that most of these also, you can weight features differently. So usually we started out with features with some sort of equal weights, and then we looked to see if some of them had greater weights and which ones seemed most important. But we do step through all of that in the Jupyter Notebook. Yeah, anytime.
How you doing? I was just wondering if you used any like feature reduction techniques such as like PCA or ICA?
We did not use any feature reduction techniques in this, other than some basic regression and saying, looking at our beta coefficient and seeing which ones seem to have the most weighting. But in general, no, we didn't for this.
So my question pertains to scoring. You opted for an F1 score. I'm interested to know why you chose a biased estimator or a biased metric. Did you consider something that was unbiased that was weighting equally a true positive and a false negative?
Honestly, I don't remember. I think that was something that one of my teammates did. However, I bet they explained what they were thinking in the Jupyter Notebook.
My question is, have you considered the interaction between your features when you do the multivariate analysis?
We considered it. We tried to look at how much interaction there was between the features, but we didn't really include it in our model analysis. That was a little bit too much for our 2-week time frame. But I agree that would be a fantastic next step.
Okay, does anybody have any more questions? Let's give another round of applause for Deborah. Thank you.